Hello, welcome to Dr. White's Fun with Graphs. In this video we are going to talk about degrees of graphs. Alright, given a vertex V, an edge is incident to V if V is an element of that edge. The degree of the vertex is simply the number of edges incident to that vertex. And we usually let d of V be the degree of V. So for instance, if we look at this particular graph, then the number of edges incident to A is 1, 2, 3, 4. So the degree of A is 4. Similarly, the degree of B is 2 because B is incident to 2 edges. The degree of C is 3 because C is incident to 3 edges. The degree of D is 3, and the degree of E is 2. The degree sequence of a graph is the ordered tuple consisting of each of the degrees. This is, of course, assuming that you have an ordering on your vertices. So if we've ordered our vertices A, B, C, D, E, then the degree sequence for this particular graph is 4, 2, 3, 3, 2. As another example, if we look at the complete graph and take any vertex in the complete graph, it is adjacent or incident to all other vertices. So there's n-1 vertices in the graph that aren't V, and it has an edge to each of them, so it is incident to n-1 edges. The degree of any vertex in a complete graph is n-1. So the degree sequence for a complete graph would just consist of seeing the number n-1 over and over n times. So for instance, the degree sequence for the complete graph K4 would be 4 threes. Now let's look at the path. So for the outermost endpoints, 0 and n-1, these two vertices are only incident to one edge. So their degree is exactly 1. On the other hand, for every vertex in the middle of the path, its degree is 2 because it lies on exactly 2 edges. So the degree sequence for a path is usually 1 followed by a bunch of 2's and then a 1. Finally, for a cycle, the degree sequence, or you can see that the degree sequence is all 2's because every vertex is degree 2 because every vertex lies on exactly 2 edges. So there's some examples of degrees and degree sequence calculations. Now, one famous lemma is called the Handshake Lemma, and it tells you a relationship between the number of edges in the graph and the degrees. It says that if you add up all the degrees of all the vertices, you get twice the number of edges in your graph. It's called the Handshake Lemma because the idea is that if you go to a party and you ask each person how many hands they shook, and you add that up, you'll get twice the number of handshakes that occurred. Why is that true? Well, let O be the set of ordered pairs, V comma U, where V is adjacent to U. So you're taking an edge and you're orienting it. So this would be like looking at a handshake and choosing one person in the handshake to be the person you focus on. Well, let's try to count the size of O, and we're going to try to count it 2 different ways. Then by our basic understanding of double counting, we must have equality between these 2 different formulas. So the first way is to first pick an edge in your graph. There are size of E number of ways to pick an edge in the graph. Then once you've picked an edge, specify one of the vertices of the edge to be the first coordinate. Every edge has 2 endpoints, so there's exactly 2 choices. Once you have done that, you've specified a unique element in O. So by the product principle, the number of elements in O is 2 times the number of edges. On the other hand, you could try to list all the elements in O by first picking their first coordinates. So pick a first coordinate, it's just an arbitrary vertex in V. Once you pick that vertex, you need to pick a second coordinate. What are the possible choices for the second coordinate? Well, it has to be a vertex U with the requirement that V is adjacent to U. How many such choices are there for U? Well, there are exactly DUV many such choices, one for each edge incident to V. And so there are DUV many ordered pairs whose first coordinate is V. By the addition principle then, the size of O is the summation over every vertex, D of V. Thus we see that we've solved the same counting problem 2 different ways, and since both solutions are correct, it must be the case that these 2 formulas are equal. Now let's apply that to our 3 favorite classes of graphs. So for the complete graph, we calculated that the degree of every vertex was n-1. Add that up over every vertex, and multiply by 1/2, and you get the number of edges. But there are exactly n vertices. We have 1/2 n times n-1. This is famously n choose 2. Which makes perfect sense because the edge set was quite literally unordered pairs. So this agrees with what our notation suggested earlier. Now for the path, there are 2 vertices of degree 1, and the remaining n-2 vertices each had degree 2. Take this sum of degrees, multiply it by 1/2, and we get the number of edges. Do the calculations, and you see there are n-1 edges, which is something we already knew. Similarly, for the cycle, each vertex at degree 2, there are n vertices. 2 times 1/2 is 1, so there are exactly n edges. Finally, if we take our other example graph from earlier, take its degree sequence, add the numbers up and divide by 2, we get 7, which tells us that there are 7 edges in this graph, which we can see 1, 2, 3, 4, 5, 6, 7. In general, this lemma is used as a useful way in certain examples to calculate the number of edges of a graph given the degrees of each vertex. However, you can sometimes draw other conclusions from it too. For instance, the number of vertices of odd degree must be even, as you can see from each of our examples. It turns out there's no graph with an odd number of vertices of odd degree, because we just showed that the sum of the degrees is twice the number of edges. So if you let O be the set of odd degree vertices, you can split this summation into 2 summations, 1 over odd degree vertices and 1 over even degree vertices. And well, if this is a sum over even degree vertices, each of these degrees is an even number, which means this whole summation is even. And this number over here is also even. And so something plus an even number is equal to even tells you that our remaining summation must also add up to an even number. But how can that be? How could this possibly be even? It's a summation of odd numbers. Well, that tells you there must be an even number of terms here, because if you add up an odd number of if you add an odd quantity of odd numbers, the result is going to be odd. So it must be the case that there is an even quantity of odd numbers.